Being okay, welcome back to 2330. It's Wednesday, September 2nd. And so what we're going to do is we're going to continue on with our chapters, and we're going to use those goal slides to draw attention to certain factors that we want to get that are, basically the foundation of adding all that extra stuff to that, either reading the book or whatever. But first we want to do a little administration, make sure everybody's on the same page, as it were. So the goal slides are also on Top Hat, and the full videos are on YouTube. And the homework for Chapter 2 will be due this Friday at midnight. Okay. Now, Monday is a holiday for us. It is Labor Day, and so we will not have class on Labor Day. Okay. So what I've done is I've taken that and I've looked at the class schedule, and so we're going to end up getting Chapter 3 done probably today, and Chapter 4 done probably on that Wednesday. So let me go ahead and pull up our a couple of new things that you'll find on the Canvas site. One of the things you'll find on the Canvas site is this right here, which is the tentative lecture and homework schedule. So what this is going to do is this is going to kind of give you an idea of what to read to. Let me admit somebody in the room here. What to read to in the book, or where you should be going with the videos. Again, the in-class, the goals thing is to get the hardest or the more complicated topic and have you a chance to give you a feedback on that, and then using the videos to fill in all the little details around those big concepts. So we'll going to do that. So if we look at our tentative schedule here, today is the 2nd, so we're going to cover Chapter 3, and Chapter 2 homework is due today. We do not have class on Monday, so we're actually only going to cover Chapter 4 and maybe a little bit of Chapter 5. Probably not. We might have to push 5 back to the next one. But that makes our homework for Chapters 3 and 4 due that Friday, September 11th. So, and then that sets the stage for our first exam on September 30th. So write that on your calendar, September 30th. We're going to do our mock exams the week of the Chapter 6 in the 5th week. Chapter 2 is due on Friday. Yes. And our exam will be on the Wednesday of September 30th. And so on the 5th week, we're going to go ahead and load up our Proctorio applets and make sure that everything's working for that. Okay, in addition to that, this is actually in the file section of Canvas, so you can go download that and keep track and keep on task. But I also have uploaded, or will be uploading, I think I've already uploaded this, the Organic Nomenclature Review. Okay, we're just starting nomenclature today, so you should not know everything on this list. Don't worry about it. What I want you to do is have a study guide that as we go forward, as we learn more and more things, like for example, today, we're going to learn about hydrocarbons, saturated and unsaturated hydrocarbons. We're going to start this, and then, but this is just to have you keep track of all the different rules as we add them. Okay, I have a question in the Zoom chat about a couple questions about homework. Let's stay behind after class, and I would be happy to help you with that. Okay. And if you can't stay behind after class, go ahead and email me, and we'll set up a little Zoom lecture. Okay, so both of those are now on Canvas, so that you can download those. They're under files, and so you can use those as references as we go forward. And what might be good is if you can print up something, look at that and kind of start marking on the organic nomenclature thing. Oh, we've only been to here, and we've only been to here. And so you'll be able to build and build and build and make it into kind of a study tool that you can use toward the end of the semester. Okay. So there is no class on Monday because of Labor Day. However, I will be sending out the email with the new link for the class. And also I will be putting the Zoom link in the announcements in Canvas. So if you can't find your email, that's fine. Go to Canvas, and there should be a link in Canvas for that. Okay. I started doing that because some people were, obviously have more email than I do in lost things. So that gives you 2 locations to keep that.
I have a question.
Yes.
I can't seem to find, I went to the file section, but I don't see what you're showing that should be there, like the nomenclature and.
Okay, it is, let me hide this for a minute. The nomenclature one is not there, interesting. I didn't unload it under pages yet.
And I also don't see the tentative schedule that you have.
Okay. I just reloaded mine, and it's the organic 2330 Intro to Organic, Chem 2330 Intro to Organic files. The first 3 files there should be the lecture and exam schedule, the nomenclature, and then the third thing should be the syllabus. Okay. Try reloading the page, because I just update this.
Okay, thank you.
There we go. Okay. Any other questions before we move on to our next one? Okay, so what we're going to start with today is we're going to start with alkanes and cyclohexane. So this is our first deep dive into, let me erase that annotation. There we go. And we're going to start going into our nice organic chemistry, and we're going to start with the simplest ones, which is what we call hydrocarbons. I have a question in the Zoom chat fee. That $10 fee does cover everything for the proctorio and all of the testing throughout the rest of the semester. So all the mock tests are covered, all of the exams are covered, and the final exam is covered with that fee. Okay. Okay. So now we're starting to get into the fun part of organic chemistry, but we have to keep some things in mind, okay? It's a system, and so we need to think about it as a system. And so we're going to start with something fairly simple, and we're going to build on it and build on it and build on it, okay? So the entire semester is building on the information we've learned in these first 2 chapters. We learned about what kinds of bonds we're going to be seeing because of hybridization, and now we're going to learn about the simplest bonds we're going to have, which are those carbon-hydrogen bonds. Okay, so the 3 goals for chapter 3 are, number 1, the idea of nomenclature. Nomenclature is a system of naming things. It's a systematic way that I can take a page-long, don't worry, I'm not going to make you do it, a page-long written out name of a chemical, and I can go step by step following each one of those names and write that true chemical down on a piece of paper. And then I could give that image to somebody and they could write the name. So that's what the nomenclature is, just classifying all of the different types of things we could have in our system and having it in a nice and consistent way. Our next 2 goals are going to be physical properties and basically what kind of bonds that these kind of molecules have between each other, not within the structure, but and then a few little reactions. We don't have that many reactions for alkanes, but we're going to talk about them. Okay, so when you go and look at your nomenclature page out on Canvas, you'll see we start with types of hydrocarbons. Hydrocarbon just means it's a compound only composed of carbon and hydrogen. Okay, so that's great. We have a lot of different materials we can do with that. However, we're also going to end up adding other atoms to it. We call those heteroatoms, meaning they're different. They're different than carbon and hydrogen. So we're going to start with the basic stuff, which is carbon and hydrogen, and then eventually we're going to add on other elements. But for now, we're just going to look at those. Now, within hydrocarbons, we have 2 kinds of straight chain hydrocarbons, and then we have another kind of hydrocarbon. So we have the simplest kind is what we call a saturated hydrocarbon. Saturated hydrocarbon means that it only has carbon-carbon single bonds. The idea comes from that you can't add any more hydrogen to the system without breaking a bond. Okay, so it's saturated with hydrogen, and so it only has carbon-carbon bonds, and all of the carbons have sp3 hybridized, meaning they're all tetrahedral. Okay, now if we have a saturated hydrocarbon, that means only single bonds. that means we have a class of compounds known as alkane. Alkane, and the key here is that A-N-E at the end here, okay? A-N-E means that we have a saturated hydrocarbon, okay? So if we have an unsaturated hydrocarbon, that means we have something else going on. We have a carbon-carbon double bond or something else going on there. So that's the main difference between the saturated hydrocarbon and the saturated hydrocarbon is an alkane. Occasionally we say it's an aliphatic hydrocarbon because it doesn't contain an aromatic unit, which is a different type of hydrocarbon. Okay, so these are our 4 classes of hydrocarbons, and we're actually going to study each one of these. The first one we're going to study is the alkanes, and that's this chapter. And then we're going to add alkenes. Alkenes have at least one carbon-carbon double bond, and therefore it has a slightly different hybridization, and we do different chemistry. So we look at that separately. Now, once we go over to having at least one carbon-carbon double bond, that we call those unsaturated, because you could add hydrogen to that molecule to get to the saturated hydrocarbon. So that's why we differentiate the two, because their reactivities are different, and that that carbon-carbon bond. Now, you don't only have one opportunity for doing a carbon-carbon double bond, you can also get a carbon-carbon triple bond, okay? Or what we call alkynes. And the key word here between alkenes and alkynes is that there's an E-N-E at the end here and a Y-N-E at the end here. Okay, let me pull those up. Okay. So those little, this A, this E, and this Y are very important. It tells us the difference between the different classes. With the A, it's only carbon-carbon single bonds. With the E, we have at least one carbon-carbon double bond. And with a Y, we have at least one carbon-carbon triple bond. Okay. Now, if we take out of that and we go to one more specific thing, we call them aromatic compounds. Okay, aromatic compounds are ring-like structures, and they have alternating single and double bonds, which makes them have incredible stability and a completely different reactivity. So we completely separate those from that, and we're going to get into those in chapter 9. Okay, so the key here is that we have these ANE compounds. ANE compounds only have carbon-carbon single bonds, and that's where we're going to start. So we'll understand how to name things. And then as we go to alkenes and alkynes and everything else, we'll add that level of complexity as we go. Okay, so let's start with those saturated hydrocarbons. Only carbon and hydrogen and no double bonds. All right. So the first thing to think about is all the carbons are sp3 hybridized. That means it has 4 bonds that it makes. And because of those 4 bonds, it's a tetrahedral geometry. And therefore, all the bond angles are trying to be 109 degrees. If groups get bigger or smaller, it's skewed a little bit, but it's that. Now, this is what a stick and ball structure would look on it. And when we think about this, the little spheres that only have 1 bond to them are the hydrogens, okay? Because they only have 1 bond to hydrogen. And the spheres that have the 4 things bonded to it are the carbon. And so whenever we see this ball and stick structure, we think of a saturated hydrocarbon. Now we're going to draw it a different way. And when we draw it a different way, we're going to leave out the hydrogens and only show where the carbons are by having the bonds in between the carbons. Okay, but so we'll start thinking about that this structure here is equivalent to that structure there. Okay, when we do oops, I gotta admit into the waiting room here. When we look at these alkanes, we typically represent them as a line drawing because it takes a lot of time to draw all the spheres and get all the angles right and trying to get all the 3D. So we actually simplify the system into what we call a skeletal formula or a line angle formula. So the way we identify that is that each line represents a single bond between 2 carbons, okay? And the end of each line represents a CH3 group, okay? So we assume there are hydrogens filling all the possible spots available to it. Each vertex or angle represents a carbon, okay? So when we look at this ball and stick structure right here, we have a total of 1, 2, 3 carbons right here. And again, to draw all of those spheres, we have 3 carbons plus we have 8 hydrogens, and we'd have to draw all of those and try to get that 3D perspective, okay? But it's equivalent to this structure here when we just go, here's 1 carbon, here's 2 carbon, here's 3 carbons, boom, boom. And we assume, unless otherwise noted, that the remaining bonds are hydrogen, okay? And this particular one has 3 carbons in it, and it'll have a specific name, and we'll get into the name here. But if you have already read ahead, this is what we call propane. So by adding another stick to the structure, you've added another carbon to the structure. And likewise, as you go to bigger and bigger. Okay, so we have to understand that this is a carbon with as many hydrogens on it as can be. This is a carbon with as many hydrogens on it as can be. And that these 2 carbons are bonded together. Okay, so that's the representation I'll be using throughout the rest of the semester to give us a fast way to draw our chemical structures. Okay. Oops. Now, the name for the compound is based on the number of carbons in the longest chain. Okay, so the name we give for each of these chemical compounds is based on the number of carbons. So you count the number of carbons in your chain, and then you know that that is going to be your name. Okay, so the first 4 are a little bit hard because they don't really kind of follow a pattern, but after that they follow a pretty decent pattern. So the first one, if we just have 1 carbon in the system, the base is called meth, and so because we have an alkane, we call it methane, okay? By adding a second carbon, we get to an ETH or an F, and so we have it as ethane because it's a saturated hydrocarbon. 3 carbons is propane, and 4 carbons is butyl. Now, after that, it starts getting very systematic in a very consistent way. We have penta, hexa, hepa, octa, nona, and decane. These are similar to Greek or Roman numbering systems, so it's pretty consistent with those. Now, once you go over to 11, you have un, meaning 1 decane, so 1 plus 10, 11. Dodecane, 2 plus 10 is 11. Tridecane, 3 plus 10 is 13, etc. And it goes all the way up. And the last one you really need to know is icosane. Icosane is 20 carbon chain. And that's where the main chain is 20 carbons, no side things. It's just a continuous carbon chain. Okay, so you will have to remember these because they're slightly different and know the method for getting all the way up to icosane. So what this also tells us is that we have a generalized formula that tells us we have a linear alkane, okay? And we know it's fully saturated because we can calculate out the number of hydrogens and carbons in each chain. So let's look at that equation right up here at the top here. So in this case, N is however many carbons you have. So in this case, we have 1. And then the number of hydrogens to have a saturated carbon is going to be that number of carbons times 2 plus 2 more hydrogens. So in the case of methane, we have C1 plus 2 times 1 plus 2 means methane is going to have the formula of C1H4. And we see that. So you can do that calculation for each and every one of these. And so this is how many hydrogens we'll have depending on how many carbons you have. Note, this changes when we have rings or when we have double bonds. So this formula only works for linear alkanes. Okay, so So up to now, we were just talking about these straight chains that were all had but that is not really representative of all the different chemicals we have possible. So we have what we call isomers. Isomers are different molecules from each other. They are either different in space or they are different in how they're hooked together, okay? So when they're different in how they're hooked together, we call that a constitutional isomer, meaning that they have all the same atoms available to it. However, they are hooked in a different way, and when they're hooked in a different way, it has a different name, and it typically has different properties as well, okay? So if we look at methyl, ethyl, and propyl, those are 1, 2, and 3, we really don't have any constitutional isomers because there's no other way to hook them together, okay? So the first one where we get to a constitutional isomer would be butane, okay? So the simple straight chain one that we saw on the previous page would have this formula of C4H10, okay? And in the straight chain, it has no branches. All the carbons look about the same. However, if we were to take this bond here and move it to over 1 carbon, we end up with the constitutional isomer of this. And so this now, because it's no longer that straight chain, it has a different name. And one of the cool things about this is we'll find out that it changes the physical properties as well. Having this straight, long chain like this allows them to lay on each other and get a lot of overlap from surface area, and it gives it a certain boiling point. But when it gets more spherical, we don't have as many of those interactions, and it changes the properties. And we'll talk about that on the goal 3. Okay, so why do we care about constitutional isomers? Well, with one atom, we really don't, because we don't have any opportunity for that. Once we got to 4, we actually had 2 constitutional isomers. If we add 1 more carbon, we can then get 3 constitutional isomers. By 10, we have 75 different isomers possible. That's just carbon and hydrogen, and just hooking the different parts up together. So if you get to 25 carbons, you're actually looking at 36 million different varieties of ways you can hook those 25 carbons together and still be a saturated hydrocarbon. Okay, so this is why it's important that we learn how to name them in a nice and systematic way. Okay, so we have, for the simplest ones, we have what we call a prefix and a suffix. Okay, the prefix is the first half of the word, the suffix is the end of the word, okay? And so when we have just straight chain hydrocarbons, we only have to care about the number of carbons in the chain and whether or not there are double bonds or triple bonds, okay? So if we look at the number of carbons in the chain, that's based on those names: methane, ethane, propane, etc. Okay? So let's look at those prefixes and look at that naming system here. This should start to look a little familiar because we just did this before, but 1 carbon has that meth as the beginning of the word, okay? And then we have eth, prop, and bute, and then we have the nice penta through deca, and these go all the way up to icosane. All we're doing is adding 1 atom, and that's changing the name. Okay. So if that's the beginning of the word, and we only have a straight chain and only single bonds, we can now add this ane at the end of it. A-N-E means you only have those single bonds between carbons. So we have whatever we have before, tridec, and then we add A-N-E to it, and that means we have that hydrocarbon. We have now properly named that straight chain hydrocarbon with 13 carbons, okay? So that's the first step in this nomenclature system, is we find the longest unbranched chain, and then we find out what is the nature of the carbon-carbon bonds. If we have any double bonds in our system, we have to change the suffix. Okay, but we're talking about alkanes, so we're going to have our suffix, our end of the word is going to be about the same for all of these. Okay, so here's our nomenclature rule. First rule is you find the longest carbon chain, okay? That's going to give you that prefix name, how many carbons are in there, okay? If you have a branch on your chain, meaning that you have some other substituent hanging off that chain, then that is called a substituent, and we have to change the way we call that substituent. Okay. So let's look at this example here. Okay, so in our compound here, okay, and this is drawn out with all the hydrogen on it so you can see, but this is the skeletal structure that I want you to get used to watching that. We have a total of 9 carbons in our chain. So this is technically, you know, C9H20, okay? However, this no longer has all 9 carbons in the same chain. So that means that remaining carbon here is now what we call a substituent, okay? So basically it has branched off from the main chain, okay? When we have a substituent, we have to name it differently to show it is a substituent. And so when we have these groups on the side, we call them alkyl groups. What's interesting about this alkyl here is that YL at the end here. Because to name that substituent, all you do is you take the number of carbons in that chain. So for example, if it was 1 carbon, it would be meth. And then you add YE to the end of it, and that makes it well known, it makes it obvious to anybody reading your work that this is a substituent on a larger parent chain, okay? So this is our first rule, is you find the longest chain. Second rule is we identify our substituents, and then we make sure that we count how many carbons are in there and identify them as that length of chain, and with the YL, it means it's a substituent. In this case here, we have a total of 8 carbons in our main chain. So that gives us our octane, because 8 is octa, and tane is because we have no double bonds. And we have methyl is the substituent. Now I'll get into why it's named, why the number's there next. Okay, so because these smaller substituents are really, really common, we have common names for them. And these common names are used a lot in the naming them. So these are things you will have to remember, but some of them are kind of simple, and but some of them have unique shapes, so they're easy to remember. So with just 1 carbon chain, it's the methyl with the YL on it right there. 2 carbons, was ethane, but now it's ethyl right here. And with 3 carbons, it's propane, and so we change it to propyl. Okay, now, all 3 of these only have 1 isomer possible. So we don't have to choose about a special one. Okay, but once, these don't have isomers. If we have this isopropyl, we still have 3 carbons in this chain here, but instead of attaching it to that main chain on the end of that chain, we're attaching it to the middle of the chain, okay? So while we don't have a constitutional isomer associated with propane, we do have a substituent isomer, propane. And when we have that, it looks something like this right here. If we were just drawing the stick structure, and then this would be your main chain right here. It's got that little Y thing looking. We call that the isopropyl, okay? Because the propyl is the straight one, and this is an isomer of the propyl because you're hooking it to a different spot, okay? So whenever we have this little Y-shaped substituent, it's the isopropyl group, okay? Now, once we get to butane, remember we have isomers available to us there as well. So if we have just a straight chain 4 carbons as a substituent, we call that the butyl group, okay? So it's just the butane, add the YL. Now, If we change the configuration so it looks a little bit like that isopropyl group, it has that Y, and then another carbon, and then we have it hooked to our main chain, like that. We call that the isobutyl group, because it looks a lot like the isopropyl, but it has one more carbon on it, okay? So it has this the Y shape at the end, and then it's hooked to the other side, the last of the carbons. Now, we could also change where we attach that to the main chain. And if we don't attach it to the first carbon, we attach it to the second carbon, we get what we call sec-butyl, okay? So if we look at the long, what that looks like drawn out, it's something like this, okay? So sec, it's attached to the secondary carbon on that butyl chain, okay? So, or the second one over. Now, the last isomer we have available to us as a common name is what we call T-butyl or tert-butyl. What that stands for is tertiary. What that means is that our carbon that we're binding to our long chain here has 1, 2, 3 methyl groups on it. So it has 3 carbons bonded to it, and that makes this having, it's tertiary because it has 3 carbons bonded to it. And we'll get into another definition of primary, secondary, and tertiary as well. But, so what this looks like in stick figure is it's typically drawn like that, and then you have some kind of main chain over it. So it's this tert-butyl group. Okay. So these are the only ones that I think that you need to memorize because they're going to be used again and again. There's a couple other ones that are like neopentyl and isopentyl and stuff like that, which we're not going to use. We're only going to use that set. Okay, so let's go back and start our rules again. Okay, the first rule was find the longest chain that is a single carbon chain without the branches on it, okay? And that becomes the parent chain. Okay, then we look for all the little branches. Okay, so we have our parent chain as the longest chain, and all the substituents have names. Okay, so now we have to give a name, those substituents names, but we also have to give them a number. We have to locate them exactly right. So we have a rule for locating the substituents. And basically the idea is we try to give it the lowest number possible for a single substituent and the lowest set of numbers for multiple substituents. Let me explain that a little bit more, okay? So in this example here, we have methyl pentane. So we have 1, 2, 3, 4, 5 carbons is our longest chain. And then we have a methyl group hanging on, right? So our main chain is our pentane chain because it has 5 carbons, and our substituent only has 1 carbon. Therefore, it's a substituent and it's methyl with a YL. Okay. Now, we can number this chain 2 different ways. We can go 1, 2, 3, 4, 5 like this, and what that would make the substituent on the number 4 carbon. However, our rule is to have it be the lowest number possible. So we actually need to number it the opposite way to try to get to the lowest number. So if we numbered it from this side here, from 1, 2, 3, 4, 5, we'll see the substituent is actually on the 2 carbon. If we numbered it this way, our substituent would be on the 4 carbon, okay? So we want to have that number be the lowest number possible. So that makes this 2-methylpentane the correct name. Okay. Now this is going to be true when you have multiple substituents as well. You try to get that lowest number on the substituent. Okay. Now, what if you have 2 substituents? Okay. Well, we're going to try to follow the same rules. We're going to try to find the longest chain. We're going to try to identify the substituents we have, and we're going to try to get them to the lowest number possible. Okay. However, if they're identical, that means you can use them as di, tri, or tetra if you have 2, 3, or 4. Okay. And that way it'll be easier to assign. But you still have to assign the number that each of those substituents is on. And we still have to follow the rule of having the smallest number possible first. Not the sum of the numbers, just the smallest number first. Okay. So in this case here, if we number our system right here from 1, 2, 3, 4, 5, 6, that's our longest chain. So we have a hexane, and we have a methyl group and a methyl group. So we can go to dimethyl, because we have 2 methyl groups right here. But now we have to identify. Okay. So if we used the numbering system we have here, we would have a 3 and a 5. However, that's not the correct answer, because if we changed our numbering system and did it 1, 2, 3, 4, 5, 6, our first substituent would be on the 2 carbon. Okay. So let's look what that looks like here. So in this case, we've numbered them from right to left, and it puts the first substituent on the 2 carbon. In this example, we've numbered from left to right, but it puts the first substituent on the 3 carbon. Okay, so that means this 3 is higher than 2, which means it can't be the right name. And so our correct name is going to be 2, comma, 4. Okay, that comma is important. It's showing identification of each of those methyl groups. One of the methyl groups is on the 2, comma. One of the methyl groups is on the 4, dash, saying that it's attached, dimethyl, and hexane. Okay.
I have a question.
Yes.
Okay, so are we supposed to order them backwards, and that is the, like where we put the, like you said, if we order this backwards, you know, there's the 2 and the 4, like in the one that you've shown us, but if we go from 1 to 6 and we put it on the 3 and the 5, that's not correct. So are we supposed to order them backwards?
It's not about ordering backwards or forwards. It's you have to number the parent chain so the first substituent is on the lowest number possible.
Oh, okay.
Okay. So and you know, we get, oh, let me add somebody here. So we're just trying to get that first substituent on the lowest number possible.
Okay, so if you ordered it forwards to backwards, and if it was on the 2 and the 4 for that one, but then you ordered it, you ordered it, if you order it like you did 1, 2, 3, 4, 5, 6, and it was on the 3 and the 5, let's say for the first one, then it wouldn't be correct, because if you order it backwards, it's on the 2 and the 4, which is smaller than 3 and 5.
So what I suggest is that you number it one way, and then you number it the other way and see where your first substituent is. Whichever one is on the lowest number, that's the numbering system you use.
Okay.
Okay.
I also have a question.
Okay.
So for dimethyl, since there's 2 methyl groups, if they're on the same carbon, is it also dimethyl?
Yes, and you have to identify where each of them is. So you would go, if they were both on carbon, we would say 2, 2 dash dimethyl hexane. Okay.
Okay, thank you.
Always identify each. So if we had 3 of them, we have to have 3 numbers there, identifying where each of them is. Okay.
Thank you.
Okay. Now, if they're not identical, we have to worry about alphabetization. Okay. So that's our next rule, actually. So if we have 2 different substituents, we still want to number them such that the first substituent, irrelevant of alphabetical order, is still on the lowest number possible. Okay. So in this case here, we have a main chain that has 1, 2, 3, 4, 5, 6, 7 carbons. So we're going to call that heptane. Okay. And we have 2 substituents. We have a methyl substituent and we have an ethyl substituent. Okay. So if we number that, we have that. So let's do it in this order here. We have the first substituent on a 3 and the second substituent on a 5. Okay, let's number it the other way to make sure. Okay, so if we number it in the opposite direction, that's this way here, we get the one substituent on a 3 and one substituent on a 5. Okay, ooh, so the numbers for the substituents are exactly the same. Okay, so it doesn't matter which way we number it for this particular example. Okay, but because of we have an ethyl group, which has an E in the beginning of it, a methyl group, which has an M, we would actually order them such that the alphabetically ordered substituent comes first and it gives the lowest number. Okay, so in this case, it would be the 3 ethyl, 5 methyl heptane. Okay, now that's only if both of the substituents are on the same numbered carbon. Okay, if they were on different numbered carbons, you always go with the lowest number. Okay, so now we're going to add another rule. The prefixes, if you have a dimethyl something, the di doesn't count toward alphabetization, only the substituent. Okay, unless you're talking about something that has a special name, like one of those special names like isopropyl, then you use the word. Okay, so let's use that as an example here. So we have, this is our parent chain here. So we have 1, 2, 3, 4, 5, 6 carbons. So we could have 5, 6 carbons. Okay, so we still have the longest chain we have as possible 6 carbons. So we should end up naming it hexane something. Okay, now let's start numbering that. So if we number from 1, 2, that puts these methyl groups on a 2 carbon. Okay, if we keep numbering it this way, this methyl group's on a 2 carbon. Let's name it the other way, just to see where the substituent lies. We have 1, 2, 3. Ooh, the first substituent will be on the 3 carbon. Okay. So we have to number it from the position where our first substituent is on the lowest number. So that means our methyls are on our lowest number, okay? So that means we have to number it from this side. 1, 2, 3, 4, 5, 6, okay? So, and that's how we have it numbered here, okay? Because our first substituent is on the lowest number. Now, we have to take into account alphabetization of the groups to tell us which group is first, okay? Notice that in this case, the ethyl group is alphabetically comes before methyl, and therefore we have to label it at the beginning of the name. And so we have 4-ethyl. That signifies that this ethyl group is on the 4 carbon. And then we have dash, signifying we have another substituent. 2, 2 dimethyl. Notice the di is not included in the alphabetization. And then our main parent chain, hexane. Okay. And that's all because our first substituent was numbering it in this direction. It would have been a 3 if we numbered it the other direction, but we still alphabetize our substituents. So the correct name here is 4-ethyl-2, 2 dimethyl hexane.
I have a quick question.
Yes.
Why is there what in the name where it says 4-ethyl-2? What does the second -2 represent?
Okay, so this methyl group is on a 2 carbon. This is the other methyl group. We still have to identify where it is. Okay, because this methyl group could actually be on the 3 carbon, and we'd say 2-3. So one of the methyl groups is on a 2, and now we're signifying the other methyl group is also on the 2 carbon. Does that make sense? So if we moved this methyl group to a 3, it'd be 2,3-dimethyl.
Oh, okay. I understand now. Okay, I just was looking at it kind of differently.
Yeah, and so yeah, that's, you know, our rules in order will help you. Try to keep these all in order, and it gets more complex as we go. But if we follow them in order, we get to the right answer. Okay, so now let's talk about the different kinds of carbons we have. Okay, they're called classifications of carbons, and The 4 classes are primary, secondary, tertiary, and quaternary. Okay, all that means is how many other carbons do you have bonded to your carbon? Okay, so if we have a carbon that's only bonded to one carbon, one other carbon, we call it a primary, or it has one carbon attached. So most of the time you see, when you see a primary carbon, it tends to have 3 hydrogens attached to it, okay? Because it needs a total of 4 bonds, and so 1 carbon, 3 hydrogens, it is a primary carbon, okay? A secondary carbon is one that's just bonded to 2 other carbons, okay? So what we see there is that we'll have something like a CH2 and then a carbon on one side and a carbon on the other. That's a secondary carbon. And then we can make it a little more complex, add 3 bonds to carbon here. And let's do a different color. These 3 bonds to carbon makes it a tertiary carbon. And then the most one is the one with 4 carbons on it and has no hydrogens. It's called a quaternary orbital. So the reason we classify these things like this is that we have different reactivities, and they have different number of times they can react. So just think about it. Primary is 1 other carbon, secondary is 2 other carbons, tertiary is 3 other carbons, and 4 other carbons. Okay. Okay. All right, that takes us now into the next set of saturated hydrocarbons we're going to talk about. So these were all straight chains that had groups on them, okay? Now we're going to talk about what if we took a straight chain and took away 2 hydrogens and linked it together in a ring, okay? We call these cyclo alkanes or cyclic alkanes, okay? Now notice, because we took this long chain, took 2 hydrogens off the ends, and made a new carbon-carbon bond there, we've changed the number of hydrogens it takes to be a saturated cycloalkane. So our equation changes slightly. So before, for our straight chain, it was CN H2N plus 2, because those are those last 2 hydrogens at the end of the chain. We've removed those when we do our ring, so we don't use that in our, we just end up with the 2N. So if you have 12 carbons, you have 24 hydrogens in your system, okay? So the way we look at that is that these are rings. And so what the way we're gonna do is we're gonna name it for the number of carbons in that ring, and we're gonna have to add the word cyclo to the front. So if we have 6 carbons in a ring, and we have to call it cyclohexane. 5 carbons in the ring, cyclopentane, etc. Okay. So when we have a ring and we have a substituent on it, and we only have 1 substituent on it, we can assume it's the 1 position, because a ring is the same all the way around, right? So 1 is 1, it doesn't matter where you start numbering it if there's no substituent on there. So if you put 1 substituent on there, you have to number it from that substituent. And then if you have 2 substituents, you want to have the lowest number and the substituent of lower alphabetical order. Okay, so we're going to do a couple examples. If you have 3 or more substituents, you want to get the lowest set of numbers. So let's look at some of those rules here. All right. So again, we're looking at the skeletal drawings. Assume there's hydrogen everywhere. There isn't a carbon bonded up to 4. Okay? So in this case right here, we have our parent is the ring right here. And our ring has 5 carbons in it. Okay? So we call that a ring is cyclo and then pentane for those 5 carbons. So this is our only substituent. Okay? And it's one of those special ones we have to remember, isopropyl. And so we don't have to say 1 isopropyl because we only have 1 substituent. So our full name is isopropyl cyclopentane. Okay. So now when we have 2 things on there, we have to label it in alphabetical order. Okay. So let's look at this one down here. So we have our main ring is the 6 carbons in a ring. Okay. So we have to name it for the 6 carbons, so it's cyclohexane. And we have 2 groups. This is one of those ones we have to remember, isobutyl and then this is a methyl. Okay, so isobutyl comes before methyl in a alphabetical sense. Therefore, it has to be 1 isobutyl dash 2 dash methyl cyclohexane. The second dash here, this dash right here is only there because it goes down the line. You do not need that dash between the methyl and the cyclohexane if it all fits on one. Let's apply that rule to our compound up here. We again have 6 carbons in our ring, okay? And we have a tert butyl group, but see the tert is in italics there? It does not count for the alphabetization. If there's a hyphen in it, like this, it doesn't count for that. But if it's all one word, like the isobutyl, it does count for alphabetization. So that's one subtlety that you'll see. If this dash is here, that means you have to use the butyl for the alphabetization. Okay, so if that's true, that means this tert butyl is the first group, and it's labeled as our 1, and that makes our other one, this is 1, this is 2, this is 3, and this is 4. So that gives us 1 butyl 4 methyl cyclohexane, and it's the tert butyl. All right, so if they're both on the same carbon, they're both 1s, but we have to identify that. Okay, so we have 3 carbons in a chain, so that gives us cyclopropane. And then ethyl comes before methyl, so we do 1 ethyl, 1 methyl, cyclopropane. All right. So that's how we name all of our alkanes and our alkyne. All of our alkanes and cycloalkanes. Now we want to add one more layer to our nomenclature, and we call it the prefix, the infix, and the suffix. Okay. So in the case of the prefix, that's what we started with, meth or eth or propyl. It tells you the number of carbons in the parent chain. Okay. So that's the first thing we do. The infix is what we were saying the AN was in ANE for our hydrocarbons, because that is the AN tells us what kind of, do we have only single bonds in our system. And then the last one is actually the suffix. And in the case of our hydrocarbons, that E at the end tells us that there are no other functional groups. Okay, so the prefix is the number of carbons in your parent chain. The infix is AN, EN, or YN if you have single bonds, 1 or more double bonds, or 1 or more triple bonds. And then the E at the end tells you have no other functional group available. So let's apply these rules. Okay, so in the case of something simple like a straight chain hydrocarbon, so if we started with something like, where's my pen? There we go. This right here, 1, 2, 3, 4, 5, 6. So we had 6 carbons there. Our prefix is hexa, okay? And there are no double bonds in this chain, so it'd be hexa with an A, N in it, and there's no other functional group, so it's ANE. So that would give us hex, AN is our infix, and E tells us we have no other functional groups. So our name is hexane. Okay. So that's for all hydrocarbons, we'll have that E at the end. Okay. So let's change it, and let's say we add an OH to the end, right here, okay? So what we'll see is we still name it for the parent chain, so we still get the hex. We still don't have any change in the carbon-carbon bond, so it'd be ane, but we have to add the new end group. We drop that E, and we add an OL to show that we have an alcohol on our system. So we're still following all the rules, number of carbons, carbon-carbon single bonds, and then whatever functional group it is, okay? And then what we'll do is, as we go through this, we're going to add more and more functional groups to our system, and all we do is we tack that name on the end.
Can you re-explain hexane again? I know that hex is 6, so it's the 6 carbons, but why do we put the AN and then the E?
Okay, so let's draw that structure again. That's a great question. So if we had 6 carbons and we only had single bonds, okay, so we get the hex from having 6 carbons. We get the AN from having only carbon-carbon single bonds. And we get the E at the end for being a hydrocarbon.
Oh, okay, thank you.
Now, if we added a double bond to it, we would still have the hex for the 6 carbons. We would have to change this to an E because now we have at least 1 double bond. And we still have an E at the end because it's still a hydrocarbon. Now, if we took the same compound and added something else to it, that end would change because we added a new functional group. So we still have our hex, our prefix. We still have our infix telling us carbon-carbon, single, double, triple bond. And then that last bit tells us what other functional groups there. Does that make sense?
Yes, thank you.
All right, and that is the basics of nomenclature for our goal 1 for chapter 3. Okay, so we're looking at 1:26, we're on time. So let's go ahead and look at goal 2. Goal 2 is a little bit shorter. What we're gonna talk about is physical properties and bonding. So this isn't like a carbon-carbon bond we're talking about. This is the interaction between 2 molecules. Okay, so we're gonna see how that interaction between 2 molecules changes their physical properties. Okay, so alkanes, by their nature, have only carbon and hydrogen bonds, right? And the carbon bond and the carbon-hydrogen bond is pretty nonpolar. It's almost completely nonpolar because the electronegativity of carbon and hydrogen are only 0.03 apart. No, 0.3 apart, sorry. So that we consider that a nonpolar bond. So that means we don't have any kind of natural polarity in the molecule. Okay. So what that means is that when a molecule comes near another molecule, it induces a temporary charge. Okay. So what it says is that as these electrons come toward this molecule, it's going to say, well, okay, I can shift some of my electrons to the backside and give me a slightly positive charge, and accept that some of those negative charges on this side of my molecule. This is what we call dispersion force. It's the weakest intermolecular force we're going to deal with, and it's temporary. It's only as you squeeze molecules together. Okay, so it's very weak and very temporary. Okay, so when we look at that with our alkanes, because we can have them different shapes, we can have them linear and drawn out, or we can actually have isomers where we have lots of branching, that's going to change the interaction from one molecule to the other. Okay, so, there we go. So in the case of these straight chain molecules, the boiling point or the melting point of these materials, number 1, goes up with each carbon you add, changes the boiling point, just because you've added mass to the system. Okay, and then we look at the different interactions the molecules have with each other. Hydrocarbons only have a weak induced force. So that means that they are going to tend to have the lowest boiling points and melting points of any class of compounds we're going to see. Okay, so boiling point is literally defined as how much heat you need to add to it to take it from the liquid to a gas. Okay, so that means that all low molecular weight alkanes, things that are 1 through 4, are gases at room temperature. So methane is natural gas that runs through the pipes. Propane goes in your grills. Butanes are in your lighters, and they all boil at below room temperature. Now, once you get a little higher, just because you're adding molecular weight, you start getting higher and higher boiling points until you get to high enough boiling point that these actually start to become, they can start to kind of stack together on themselves and become waxy solids at room temperature. So think wax or candle wax, etc. So we have these gases that are at room temperatures, these liquids that would be like gasoline or solvents we use. And then once they get too high, they become more solid-like and more waxy until you get to really, really high molecular weights, which we'll talk about in chapter 15, where we end up with something like polyethylene. That's basically like a million molecular weight or hundreds of thousands of atoms long material, and it becomes this solid material at room temperature. Okay, because of the only carbon and hydrogen bonds, it actually has a fairly low density. So it literally floats on water. All of the hydrocarbon liquids and solids float on water because of that low density. Okay. Now, I alluded to this before. We had a question before, and we were looking at what drives some of these physical properties, and it has to do with that weak induced force. Okay, so if we have long extended chains and they have weak force, you have enough surface area to have it interact several times throughout the molecule. Okay, this means it's going to have more London forces than if it wasn't long and extended. So what we see is the longest, straightest chain hydrocarbons tend to have the higher boiling points and melting points for the same molecular weight. Okay. Now, just by adding one little branch to the system, we actually disrupt the system enough to change the boiling point and melting point. So for example, hexane right here has a boiling point of almost 70 degrees, okay? Just by adding one little bump on that chain so it can't stack as well, we lower the boiling point by 5 degrees, okay? And if we are to take that and move that around such that it makes it even harder, so we've put the bump in the middle and that lowered the boiling point by 5 degrees. Let's put it toward the end. That's going to lower the boiling point by 2 more degrees. And let's take, again, the same molecular weight of 2 different compounds, different isomers. They're starting to move those functional groups so that we have a more and more ball-like molecule. As you get more ball-like molecules, so now you have a spherical molecule coming next to a spherical molecule and very little interface between them. So as molecules get more branched or more spherical, their boiling points go down for molecules that are exactly the same weight. So when we're looking at these things, the first driving force is molecular weight. The second driving force is how much surface area the molecules have. Oops. All right, and that takes us to some of the most common ones we have are like natural gas, which is mostly methane. We have our liquids that we can get from distilling propane. And then actually coal is a very high molecular weight material that is mostly carbon and hydrogen with a few other elements thrown in. And it is mostly carbon and hydrogen, and it has such a high molecular weight that it is a solid. Okay. And so if you've ever seen those distilling towers as you drive through Houston and they look really tall and there's the flame coming off the top here, what's really happening in there is they're taking the crude oil that they pump out of the ground and then they heat it up. And so by the different molecular weights, they go up different parts of the tower, okay? So the lowest one is stuff that you would use for putting oil in your car, the lubricant in your car. And then there's fuel oil, which is used specifically in mostly the East Coast. Then we have kerosene. Kerosene and jet fuel are very similar in their makeup. And then we have gasoline, and then we have all of the smaller gases are either used to make other industrial materials or are burned off as excess. All right, questions on these properties. So number 1 is the molecular weight. Number 2 is surface areas because of that weak dispersion force, or it's a weak induced dipole force. Okay. And that brings us to our last goal. And there's only 5 slides on our last goal. Our last goal is reactions. Now I said that hydrocarbons actually don't have that many reactions to them. And so what we'll see is that that's a good reason to start with them because, you know, we're going to start with simple reactions and we're going to add to them as we go. Okay. So if we look at our 4 classes of hydrocarbons, the one we just talked about, the alkanes, are saturated. They don't have any double bonds or triple bonds. Double bonds and triple bonds are more reactive and can do more things. The arenes are actually less reactive, but do different chemistry. Okay, so one of the few reactions that alkanes do is they do what we call combustion. Basically, they burn. Okay, so we can take these hydrocarbons and burn them with oxygen, and we'll generate CO2 and water. Okay, now how much heat comes out of it depends on how many bonds you're breaking. So if we have methane, we have 1 carbon and we have 4 hydrogens. And so we have a total of 4 bonds that get broken and remade during the combustion process. When we do that, we get a certain amount of heat out. Okay. So in this case right here, if we measure the amount of heat given off by the reaction, it's something like 212 kilocalories per mole. Now that's heat released during the combustion process. Okay. Now, if we take propane, right here, it's got 3 carbons. We take 1 equivalent of 1 mole of propane and burn that. We actually see about almost twice as much energy is given off because more bonds are breaking, more bonds are being reformed, and therefore the same amount of methane, the same number of moles of methane, actually has far less energy than propane. That's one reason we use propane in our grills, because of energy density. It can actually pack more heat into a smaller space. Okay. So again, combustion is one of those few reactions that it does do. Okay. The other weird thing we can do with this is we can actually use it to disproportionate to give us other materials out. And we call this syngas. Basically what we're doing is we're using carbon or hydrocarbons to give away part of their materials, and actually instead of generating water like we saw in combustion, we're actually generating hydrogen. So hydrogen is a nice combustible gas, and it's used in a lot of energetic systems. And so we can actually take coal and heat it, superheated with water, and we're going to generate a gas, carbon monoxide, and an equivalent of hydrogen gas. And this is called the syngas process, or synthesis gas. We can do the same thing with methane. It takes a little more heat and a little more catalyst, but you still get into that same disproportionation to have the oxygen bind to the carbon and generate an equivalent of hydrogen. Okay, so we can then take that syngas we just made that has carbon monoxide and that hydrogen and actually convert it into something else that has a higher functionality. So for example, in the case of methane, methane really only burns. We can't do any other reaction to it except for kind of convert it into this gas. Okay? So if we just take this gas and add a different catalyst to it, we can make it produce a liquid fuel, methanol. Okay? Or if you can, and then if you take this methanol and add a little more CO2 to it, you make another commercially viable compound called acetic acid or vinegar, concentrated. So again, hydrocarbons don't do very much. All we really need to think about is, okay, they burn, and we can use them to make other things. Yeah, and that's just an extra slide for that we, as we move to other hydrocarbons, as the oil gets consumed, we're going to stop using it as fuel, and we're going to use all the oil for other chemical processes and try to come up with a different fuel to use. All right, questions on hydrocarbons. Okay. We have naming for straight chain hydrocarbons. We have naming for cyclic hydrocarbons. We've introduced those steps, those 7 steps to naming things correctly. And we notice that they really don't do that much as far as reactions go.
I'm a little confused on, like, I don't think I can picture on the cyclo alkanes, can you just like number them on the picture?
Sure. Let me, so no, that's not that one. That's in this one.
In goal 1.
Yeah. So let me actually draw a different one that you haven't seen. And let's see, I have a blank slide here. All right. Okay, that's not exactly blank, but we'll erase that. And, okay. All right, so when naming your rings, you have really two rules. Number one, the ring is always named for the carbons in the ring, and then you add cyclo. If you only have one substituent, you only have to start there. And if you have two substituents, you do it alphabetically. All right, and then if you have three substituents, you do it by lowest number. So let's start with the simple one. This right here, 5 carbons in the ring, so it's cyclo pentane. Okay, so it only has single bonds, so it's AN, it's a hydrocarbon, so it's an E, and it's in a cycle with 5 carbons, right? So if we add one substituent to our cyclopentane, let's add a methyl group here, we then start naming it from the substituent. So we start numbering it from that substituent. So this is always going to be number 1 because you have only one substituent, so it must be in that one position. So we can just call that methyl cyclopentane, okay? Because that's the only place it can be, okay? So let's add another group to there. Let's keep that methyl group where it was, but let's add an ethyl group over here, okay? So now we have 2 groups possible, okay? So the rule tells us that number 1, we keep our cyclopentane. So we still have cyclopentane because that didn't change, okay? But we have 2 groups. So we have a choice of 1, 2, 3, or 1, 2, 3, okay? And our rule here is that we do it in alphabetical order. So ethyl comes before methyl. So we're going to put the ethyl group on the number 1. So it's going to be 1 ethyl dash 3 methyl dash cyclopentane. Okay, so let's add the last rule. Okay, the last rule is if you have 3 substituents, you don't do the alphabetical. 1, 2, 3, 4, 5. Yeah, all right, so we have 1. Let's keep our ethyl there. And then let's add another methyl here. Okay, so now we have a total of 3 substituents. Okay, so now we have to number them in the smallest numbers possible. Okay, so if we were to number this, starting over here, we have 1, 2, 3, 4. That's probably not the smallest number we can get. Let's try it numbering it something else. So let's try 1.
Can you scroll up a little bit, please?
Sorry. Yeah.
Thank you.
There we go. Let's load that up. So let's do it like this. So we go 1, 2, 3, 4. Okay, that's getting worse. Okay, that's higher numbers. Okay. So let's number it again. Let's do it this way. 1, 2, 3, 4. Okay. So now we have our first substituent and our second substituent at our lowest 2 numbers, okay? So we could also name it 1, 2, 3, 4, okay? But that will not apply, that we want this ethyl group to be on the lowest number possible while still maintaining lowest numbers. So that's going to make our best numbering system to go through our methyl group 1, 2, 3, 4. So that's the lowest number we can have all 3 substituents on and keep the ethyl group as number 1. So that's going to be 1 ethyl dash 2, 4 dash dimethyl cyclopentane. Okay, so each time you add a substituent, you change the rules slightly. Does that make sense? There will be, yes, we will be tested on naming of hydrocarbons, both regular and cyclic, and our activity on next week will also be nomenclature. Okay, does that answer your question? Okay, so these are the top goals to think about for our chapter 3 here. And so, for chapter 3 here. And so what we want to do is we want to go ahead and start applying this to what we see in our homework, and then look at the book and or the videos to add a little bit of any little details around there that we didn't quite pick up on our goal slide. Okay? So it's 1:45, so I'm going to go ahead and quit recording, but if you want to hang around and ask a few questions, we can do that.
Thank you.